We are going to use mupad to obtain approximate value of the extrema of this function. So first let's look at an easy graph of this function using Matlab. So I'm going to say symbols x and y, and then we will define our function as what that was. That was 3 plus x to the 4 plus x plus 8 times y to the 4 minus 6xy times exponential negative x square plus y square. So we shall enter the values in that we have x to the 4 plus 8 times y to the power 4 minus 6 times x times y, and then times the exponential of, and it'll be easier to write, oh no, sorry, minus 2 minus y to the power 2, and let's just hold on to it. I think we typed it correctly. All right, and we will look at an easy surf of f. Okay, and the graph should be coming up. So here is a graph for values from negative 3.5 to positive 3.5 and y from negative 3.5 to positive 3.5 of x, and in this rectangular domain what we find is that there are two maximum values, two minimum values, and then we have a saddle point. Okay, now we would like to obtain the approximate values of the max and the min. All right, and first it will be a good idea to locate approximately the intervals or the disks on which the max and min are taking places, so that we can find the approximate values. So remember, we had the graphing window as as a rectangle from negative 3.5 to 3.5, and we could see that even negative 3 to 3 are enough. So what we will do is that we will create a rectangle of a mesh grid on that, so that we can make a contour plot. All right, so let's quickly do that. All right, so here we are, and then we can let's define g as an inline function for the purpose of the array arithmetic, okay, of f. So here we have everything, the periods put in properly for array arithmetic. So now let's look at a contour plot. So we will ask for, before we do that, we have to give z the values. Okay, so we have we are going to define our z as g at xy, and then we will ask for the contour plot of xyz. Let's ask for 50 contours, and let's keep the color black just for clarity. Okay, so there we go, it should be coming up, and here it is. Let me adjust it. So here we have a contour plot showing 4 places for max or min and a place for saddle point. So we can see that we have one local max or min in this rectangle, which can be easily seen between x from negative 1 to 1 and y from, say, about between 1 and 2. Okay, so the rectangle is much narrower than much smaller than the rectangle that we took, or the domain that we took. Now we will go to mupad to obtain these points approximately, which will be a little easier. So let us open a mupad window by just typing in that mp handle equals mupad, and a mupad window will come up. So what we are going to do is we are going to first enter the expression of the function in mupad, okay, and when we have, I'm going to put a colon sign here, just trusting that I typed it correctly, okay, and in just to make sure that you are or a shortcut for obtaining everything correct, make sure that you have enabled the command bar so that you can choose the commands from the menu mostly. All right. Now to obtain the critical points, we have to solve these equations by setting the partial derivatives equal to 0. So we go back to mupad for that. So we will define the partial derivatives. So here we have fx as the partial derivative of f with respect to x, and let's put this colon here so that it understands the definition. And so there we have the partial derivative. Okay, so let me enlarge this for you, and let me do this instead of having you watch me typing. What I would do is that I would type everything in and then just come back to explain to you what I did, because all I'm doing is typing in commands. All right. So what I did was that I defined fy as the partial derivative with respect to y, and let me put this colon sign here because otherwise it will not take the value properly. So, and then remember this, that you had seen that one of the critical values is contained in the rectangle. So the rectangle that we are looking at here. So what we do is when we press the enter sign, we will see the solution. So here we have an approximation of the coordinates of xy, of the x and y coordinates of a critical point. All right. So then next, now to find an approximate value of the function at this point, we can use this eval at feature. Okay, and then once we press enter for this, okay, then what we get is, so we get an approximation of the value of the function at this point. Now we will go ahead and look at it graphically. That is what's going on here. So here I have defined a plot of f in this window as g, and you can obtain this whole thing by using the command bar. Okay, that's what I usually do. So if we ask it to plot the function g for us, or sorry, make a plot g for us, it will make a plot for us. All right, so here the plot is coming up. Now we had seen this plot already, that we have 2 max in here and 2 min, and then we have a saddle point here. So let's just make sure to see that the value that we got for the max is a good approximation. So remember, this is the approximation that we had seen for the functional value at this point. So what I'm doing is that I am going to ask it to plot this plane z equals this much for, on the top of this. So I have defined h as this plot in the same window with the same adaptive mesh. So we shall ask it to plot, just a second, plot g and h for us in the same window, and the graph will come up. So here is our plot showing that the value that we had obtained is a good approximation of maximum value, and of course if you look at the expression of the function, we have maxima at both these points. All right.